In the diagram, if you see the actual value of the data is y. We estimate a regression line and we get the point here as y hat. Now this line, it shows this is y bar, that is the mean of y. Here basically we are just changing. Earlier the line was starting from not from the zero origin, so we take the mean of x, take the mean of y, and our line is now starting from the origin, so the intercept is equal to as such 0. So this is the actual y hat is the estimated y, and this y bar is the mean values of y. So this regression line y hat is equal to alpha plus beta hat is able to explain the variation. If you see, that is the variation is able to explain this variation. Now this variation is divided into two parts. One part is explained by this regression line and is called as the explained variation. That is the small y hat, small yi hat is equal to y hat minus y bar. This portion is explained. My regression line is able to explain this portion of the variation. The second portion, that is the distance from y and y hat, the actual y and minus the estimated y, this portion is not explained. The second portion is not explained by the line, and hence we call it unexplained variation. So this is your error. Error is y minus y hat, and the total variation is summation yi, and it will always be 0. The positive values will cancel out the negative values. Now, so what we have to do, in order to overcome the issue that the positive values and all those things are cancelling the negative values, we square it. So now, instead of just discussing it as yi minus y bar, we say that the total sum of squares is equal to summation small y square, and this is equal to summation y, the actual value, minus the mean value and the square of it. Similarly, explained sum of squares, that is summation of small y hat, this is equal to the explained portion was y hat minus y bar, so this is equal to y hat minus y bar whole square. And then we have this unexplained sum of squares, this is equal to summation e square, this is equal to it was really in actual it is y minus y hat, this is the unexplained, but when we are taking unexplained sum of squares, we do the sum and we square it. So summation y minus y hat whole square. The same thing we can see from here. So the total variation summation yi, and this portion is the explained variation, this is the unexplained variation. So the error term is yi minus y hat. If we take the values of yi is nothing but, from here you can get it. From here you get, so this can be written like this. So, and y hat, it can be on the things, we can write it in terms of this. So capital Y hat is equal to small y hat plus y bar. So E, you take the value of yi from here and this y hat is from here. So error term we can write it like this. So this is small yi plus y bar minus small y hat plus y bar. So we have this formula over here. Now this total variation is divided into explained and unexplained variation. Now taking squares of both the sides, so we are taking the square of this and also taking the square of this, we get summation small yi hat yi square is equal to summation small y hat plus e the whole square. We open the bracket using the formula a square plus b square plus 2ab. So we get summation y hat plus the b term summation e square plus 2ab, that is summation y hat e. From this we write this equation as yi is equal to alpha hat plus beta hat xi plus ei. Now what we do, we add summation on both sides. We take this equation yi is equal to alpha hat plus beta hat xi plus ei. So we add summation to both the sides. This is summation y, this becomes NA, and beta hat summation x and summation e. Then we divide it by n. So upon dividing it by n, this term it becomes y bar, n cancels, alpha hat remains, summation xi upon n, it becomes beta hat x bar, and this term becomes 0 as summation e is equal to 0. So we have these two equations. The first one is yi is equal to alpha hat plus beta hat xi plus ei, and the second equation is y bar is equal to alpha hat plus beta hat x. So we subtract the second equation from the first one. So it is yi minus y bar is equal to alpha hat minus alpha hat plus beta hat xi minus beta hat x bar plus ei. So this we can write it as, this cancels. So what is left is beta hat x minus x bar plus e. So, and this is capital Y minus y bar. This can be denoted by small yi is equal to beta hat small x plus e. If you want to write it in terms of e, the error is equal to yi minus beta hat xi, small xi. Now we do some algebraic manipulation. We multiply both the right hand side and the left hand side by summation yi. So when we do that, it is summation yi hat ei is equal to summation yi under yi hat, this is the multiplication, multiplied by this term yi minus beta hat xi. When we open the bracket, we get the final last equation over here, that is summation y hat ei is equal to summation y hat yi minus beta hat summation y hat xi. So now see, we get this equation from our previous discussion, that is summation yi hat ei is equal to summation y hat yi minus beta hat summation y hat xi, all this in the deviation format. Now herein what we will do, we will be using an information yi hat, small yi hat is can be written open of the deviation form, so it is yi hat minus y bar. Now when we write the values, we can open yi hat like this, alpha hat plus beta hat xi, and y bar we can write it as like this, alpha hat plus beta hat x. Now then we move on to yi hat is equal to, when we open the brackets, there is a mistake over here, it will be minus. So we had alpha hat plus beta hat xi minus alpha hat minus beta hat x bar. So plus alpha hat and minus alpha hat, they cancel each other. So what is left is beta hat in the bracket xi minus x bar, which can be, if we write it in the deviation form, so y hat, small y hat is equal to beta xi. So what we do, we write it, we use the same information over here, and using that we can write this as like this. So beta hat summation yi xi minus beta hat summation beta hat xi multiplied by xi. So next time what we can say, we can multiply these two. So beta hat summation yi xi minus beta hat square, beta hat and beta hat square, and summation xi and xi summation xi square. This you can write it as beta hat summation yi xi minus, this is the formula for beta hat. Beta hat is equal to, in the deviation form, summation small yi xi divided by summation small xi square. So we write it like this, multiplied by summation xi. So this finally this can be again written as beta hat summation yi xi minus the above term square summation yi xi divided by summation xi square, summation xi, because one of there are two xi's beneath, because of the square, one of them this and one of this, it get cancelled, so one is left, summation xi is left. This can be written as, this is multiplied over here also, so this can be finally written as summation, we open this beta hat also, summation yi xi divided by summation xi square, this is nothing but your beta hat, and then multiplied by this term summation yi xi, and here also it is summation yi xi in the square divided by summation square, this term and this term is the same, so summation y hat ei is equal to 0. Now, so as the summation yi hat ei is equal to 0, so when we have this equation, that is the total variation is this is the total variation, this is the explained variation, and this is the unexplained variation, and this term, it becomes 0. So we can write it like this, that is the total variation is equal to the explained variation plus the unexplained variation, that is summation small y square is equal to summation y small y hat square plus summation e, that is summation e square. So we can say it simply as, that is this total sum of squares is equal to explained sum of squares plus unexplained sum of squares. Now we take this equation again and then we divide it all of them by summation yi square, or in the deviation form. So summation yi square divided by summation yi square, this also sum. Now here summation y hat square divided by summation y square, and here summation e square divided by summation y square. So this and this cancels and it becomes 1, and this is this remains the same, this remains the same. So what, upon rearranging, we can write it this equation in the terms of the explained variation. Explained sum, when we write it in terms of that, so it becomes summation y square y hat square divided by summation y square, that is the explained sum of squares, is equal to 1 minus, this is the unexplained sum of squares. So now so what is this? This we can say it as y square hat square divided by y square, that is equal to explained sum of squares divided by total sum of squares. This is nothing but the r square. Now r square is used to check how much percentage variance in the dependent variable is explained by its relationship with the independent variable. Now this we can relate it with the correlation coefficient concept. You can say the Karl-Pearson correlation coefficient. The basically it is that r square is equal to as such r square. This r square is what we get in regression. This r we get from the correlation. Now the formula for r is equal to the Karl-Pearson or the correlation coefficient formula is in the capital form, original no deviation, summation x minus x bar y minus y bar divided by under root summation x minus, this is capital X, summation x minus x bar square multiplied by summation y minus y bar square. And regarding the coefficient of determination r square, which we use in our discussion of regression, this r square is equal to summation e square divided by summation y square. This can be written as, just now we have seen this in our previous slide, that is r square is equal to 1 minus summation y minus y hat whole square divided by summation y minus y bar square. Now so we are going to prove that this r square is equal to r square. Means the small r square, that is the correlation coefficient, the square of correlation coefficient is nothing but the coefficient of determination. So the r square we can write it as summation small y hat square divided by summation y square. This is equal to explained sum of squares divided by the total sum of squares. This we can write it as beta hat xi, because we have earlier proved that summation y hat, we have earlier proved that y hat, small y hat is equal to beta hat x. Now, so we are writing this over here in place of y hat square, we are writing beta x square, and summation yi we write it as it is. So now we can say, we can take the beta out. So when the beta hat comes out, beta hat squared is multiplied by summation xi square divided by summation yi square, because the formula for beta hat is equal to summation xi yi divided by summation x square, all in the deviation form. So we open this formula and we write it in place of beta, and this was over as it is comes. So now it cancels. So now after cancelling out, what is left is summation xi yi whole square divided by summation xi square yi square. This is equal to, this is my r square, and this is also equal to your small r square. The formula for r was this. The formula for r was summation x minus x bar y minus y bar divided by whole under root summation x minus x bar square summation y minus y bar square. This we can write it, and here it was a square. So when we are removing the square, we get when we remove this square, we will get is as equal to this. So we can, this is over here written in the deviation format, and this is written in the normal x and normal y. So with this we can say that our correlation coefficient, basically the Karl-Pearson correlation coefficient, if we square it, we will get what is called as the coefficient of determination. So this was our first, we have just now completed the first one, that is the coefficient of determination is the criteria to understand, the economic criteria to say that the estimated parameter is okay. The next is the standard error test. In the standard error test, suppose say we estimate that beta hat is equal to 0.5. and the alternate hypothesis, if say the alternate hypothesis is accepted, that is H1, the alternate hypothesis is H1, beta is not equal to 0. Then we cannot say that the above statement is correct. Beta is equal to 0.5 and not equal to 0. So when we move to the standard error test, so there will be a null hypothesis and there is an alternate hypothesis. What does the null hypothesis signify? That beta is equal to 0. Beta is equal to 0 means, the null hypothesis means that beta hat or the estimates of beta has been obtained from a sample which represents a population where actual B is equal to 0. And similarly, the alternate hypothesis is beta is not equal to 0. So if in any case our first null hypothesis, our null hypothesis is accepted, that is beta is equal to 0. If this is accepted, it means if this is accepted, then it means that our population parameter, when we have estimated a sample parameter, and that is not explaining the population parameter. So that is why I give the example that if suppose it is beta hat is equal to 0.5, and if the alternate hypothesis is accepted, that is alternate hypothesis says that beta is not equal to 0. So what it means that our estimate has been obtained from such a sample where beta is equal to 0.5 and beta is not equal to 0. If beta is equal to 0, it means there is no relationship between the independent and the dependent variable. So suppose this, we now simplify it, suppose this H naught, the null hypothesis is beta is equal to 0, and the alternate hypothesis is that beta is not equal to 0. If null hypothesis is accepted, it means there is no relationship between x and y, and if this is accepted, it means no relationship, and if this one is accepted, it means there is relationship. So if the alternate hypothesis is accepted, it means there is a relationship between the two variables x and y. Now, there is a rule of thumb which says that, the null and the alternate. So if you see, if the standard error of beta hat, is less than beta hat by 2, we reject the null hypothesis. And if the standard error of the beta hat is greater than beta hat divided by 2, we accept the null hypothesis. So that was the rule of thumb. So when we want to basically test whether the sample mean is equal to the population mean or not, so we do t-test. Now t-test, the student's t-test, it is applied when two conditions are met. First, the sample size is less than 30, and the second is the actual variance, or you can say the population variances, is not known. And even if the sample size is more than 30, we are using t-test because in most of the cases the actual variance is not known. So to test this, we have this formula. The formula for t is equal to x bar minus mu divided by standard error of x bar. This we test at n minus 1 degrees of freedom, and that's it at the moment. So suppose what is our basic purpose? To test whether the population mean is equal to the sample mean or not. So for this, the null hypothesis is a bit modified, that is, the estimated beta hat from the sample is equal to the population beta. This will be the alternate hypothesis H1. The H1 will be that beta hat, the sample estimate, is not equal to the population estimate. So this is what we are basically going to test using the t-test. So now we modify. Actually the t-test was, we had this as the t-test formula. So we modify it for according to our need. So t is equal to, now we have in place of it was basically x minus mu divided by, so now we have t hat is equal to beta hat minus beta and then the standard error of beta hat, and there it was standard error of x bar. So now we calculate this t value. This calculated value of t is compared with the table values or the tabulated value. Now if we just draw this t distribution, this region is the acceptance region and this region is the rejection region, this region is the rejection region. So if the calculated value is greater than the table value, that is the t lies over here, then H naught is rejected, is not accepted. So then the alternate hypothesis is accepted. And if the calculated value is less than the table value, H naught is accepted. So here H naught is accepted, and if the t lies in the acceptance region. This also region is, we will come to a discussion of one tail test and two tail test, we will see that, but this also is the same rejection region. Here null hypothesis is rejected, alternate hypothesis is accepted. Only in this region we have, that is the null hypothesis is accepted and alternate hypothesis is rejected. So, but in our example we do not know the actual values of B. We are not aware what is the actual beta value, we are just using. So we basically test null hypothesis, beta, not beta hat, beta is equal to 0, alternate hypothesis, beta is not equal to 0. So Now it was basically the formula which we have seen over here was beta hat minus beta. So now since we don't have the value of beta, it is modified. T is equal to beta hat divided by a standard error of beta hat. And this is the modification of the t-test which we will be using over here for significance testing. This all we were doing for the regression slope coefficient. The same can be done for the intercept. So intercept h naught alpha is equal to 0. Sorry, this is h1 alpha is not equal to 0, and here the t is equal to alpha hat divided by standard error of alpha hat, based on the same reasoning. Now next is we construct a confidence interval. See, here we simply say that the sample represents the population. We say nothing about the exact level of alpha and beta. So basically we have to construct a confidence interval. We already have values of alpha and beta. So the need is to construct a range on both the sides, and the actual value of alpha and beta will be coming under the range with certain probability. Like suppose we want 5% level of significance, it will indicate that 95% confidence interval, a 95% chance that this will happen. This was our discussion on one-tail test and two-tail test. Here it is, the rejection region or the significance region is on the right hand side. Here the significance region is both on the right hand side and the left hand side. So there are one-tail and two-tail test. When we are sure about the sign of the parameters, we use one-tail test. On the other hand, when we are not confident about the sign of parameters, we conduct this two-tail test. So if the actual values lies in the region of acceptance, H naught is accepted. If you're checking at 5%, then 95% chance is that the T lies in the acceptance region. Now we will go over with the formulation of the confidence interval. So the probability 5% is equal to 5 divided by 100, that is equal to 0.05. If it is a two-tail test, we divide it into two parts, so 0.025, 0.025. So the probability that minus t 0.025 is less than the calculated value t asterisk is less than the t which is 0.025, this is equal to 0.95 for 95% level of confidence. Now this t is nothing but beta hat minus b divided by standard error of beta hat. So this can be written as, in place of t we are using this the formula. Now we just do algebraic manipulation. We take this standard error over here, so t in the lower value minus t 0.025, standard error of beta is less than beta hat minus beta, and it is t at 0.025 standard error of beta. So this goes over here. Now this we can again rearrange and write it as, this confidence interval will be the estimated value of beta minus t value at 0.025 multiplied with the standard error of beta. It will be less than the actual beta, and this will be again less than beta hat, that is the estimated value of beta hat, plus this t 0.025 multiplied by standard of error of beta. So if we know this, we can know from the t table. So when we know this the minus point, and when we know this point and we know this point, we get a range which is helpful for forming the confidence interval. So we basically started our discussion of this lecture with the to estimate how our parameters are good or not. So we have two criteria to discuss. One was the economic criteria, economic criteria. This is also called as the statistical criteria, and the second one was econometric criteria. In this discussion, we were concerned with the economic criteria. Economic criteria, we have again two. One was based on R square, and second one is based on the confidence interval. With this, I end this discussion. Thank you.